Lecture 15, Termination Detection. Preface, recap of previous lecture. In previous lecture, we have discussed the basic concepts of distributed minimum spanning trees and also discussed the algorithms, that is GHS algorithm. Content of this lecture. In this lecture, we will discuss about termination detection and a set of representative algorithms for termination detection. Termination detection based on concepts of snapshot, based on weight throwing and spanning trees, etc. These different algorithms which we are going to see in this lecture. Introduction. Termination detection problem was brought to the prominence in 1980 by the famous people. A fundamental problem to determine if the distributed computation has terminated, meaning in the sense that the distributed computation consists of the cooperation of many processors and the corresponding their communication channel. So, the distributed application which runs on different processors require to know when the entire computation is completed. This is a fundamental problem as far as distributed computation is concerned. This task of finding the termination detection is a non-trivial task because there does not exist a global time and also there does not exist a global state, and the processes, no process has the complete knowledge of the global state. In this particular setting, finding out the termination of a distributed application is a non-trivial task. A distributed computation is globally terminated if every process is locally terminated and there is no message in transit between any processes. Given this definition, locally terminated state is a state in which a process has finished its execution and will not restart any action unless it receives a message. In termination detection problem, a particular process must infer when the underlying computation has terminated, and it has a different application, it has wider application in the distributed system applications. So, introduction. Termination detection algorithm is used for this particular purpose, that is the messages used in the underlying computation are called basic messages and the messages used for the purpose of termination detection are called control messages. So, in termination detection algorithm we are going to use two different type of messages. So, the messages which are normal computation messages called basic messages, and the messages which will basically lead to the termination detection messages are called the control messages. Termination detection algorithm must ensure the following, that is, first is the execution of termination detection algorithm cannot indefinitely delay the underlying computation. Second is the termination detection algorithm must not require additional new communication channels between the process. So, that means without disturbing the underlying computation, how the termination detection algorithm works and how the termination is detected is going to be an important issue for designing such algorithms. Now, the system model which is going to be assumed in our discussion for designing the termination detection algorithm. At any given time, a process can be in one of the two states, that is the active and the idle state. So, if it is in active state, that means it is doing the local computation, and idle means where the process has temporarily finished the execution of its local computation and will be reactivated only on the receipt of the message from another process. So these states basically are not fixed, they are changing. So active process can become idle at any point of time, and idle process can become active only on the receipt of a message from any other process. Only active process can send the messages. Now a message can be received by a process when the process is either active or idle. So on the receipt of a message, the idle process can become active, that is shown here. So the sending of a message and the receipt of a message occur as atomic actions. Now we are going to define the termination detection formally. Let PIT denote the state that is either active or idle of a process I at the time instant t. Let Cij at time t denotes the number of messages in transit in the channel at the instant t from Pi to Pj. A distributed computation is said to be terminated at any time instant, let us say t0, if and only if for all processes at time t0 the state is idle, and for all the channels between I and j at time instance t0 is not having any messages. That means it's an empty channel or there is no message in the channel. Thus the distributed computation is terminated if and only if all the processes have become idle and there is no message in transit in any of these communication channel. Then the state of the global state is basically defined as the termination detection, or is a termination state. So termination detection algorithm. There are various termination detection algorithms available in the literature. So these algorithms are different based on what topology they are going to assume and also how they are going to basically address the basic and the control message flows, and without the disruption of the basic computation, how the termination is detected. So Dijkstra's algorithm is ring based termination detection algorithm that is given first in 1983. After that, Topor has given the termination detection algorithm for distributed computation that we are going to study. So there are different kind of algorithms, and Huang also has given a termination detection algorithm based on weight throwing that we are going to cover in this part of the lecture. Termination detection algorithm using distributed snapshot by Huang in 1989, that we are going to understand first. The algorithm assumes that there is a logical bidirectional communication channel between every process. Communication channels are reliable but not FIFO. So message delays are arbitrary but they are finite. Main idea of this algorithm is that when a process goes from active to the idle, it issues a request to all the other process to take the local snapshot and also requests itself to take the local snapshot. So when a process receives this request, if it agrees that the requester became idle before itself, then it grants the request by taking a local snapshot for the request. A request is successful if all the processes have taken a local snapshot for it. The requester or the external agent may collect all the local snapshot of the request. If a request is successful, global snapshot of the request can thus be obtained and recorded global state will indicate the termination of the computation. So formal description of this algorithm goes like this. Every process I maintains a logical clock, and which is denoted by x, which is initialized to 0 at the start of computation. Process increments its x by 1 each time it becomes idle. So the basic message sent by the process at its logical time x is represented by b of x. A control message that requests the processes to take the local snapshot issued by a process I at a logical time x is represented by r x of I. Each process synchronizes its logical clock as loosely with the logical clock's axis on the other processes in such a way that it is the maximum of the clock values ever received or sent in the message. A process also maintains a variable k such that when process is idle, the xk pair is maximum of the values xk on all the messages, that is r xk ever received or sent by. The logical time is compared as follows: x comma k is greater than x prime comma k prime if and only if x is greater than x prime or x is equal to x prime and k is greater than k prime. That is, if there is a tie between x and x bar here, then the process IDs are used to break this particular tie in this comparison. Now the algorithm has 4 different rules. They are the guarded actions, which basically will be activated any one of them at a particular time depending on the situation when these rules are qualifying. So the rule 1 says that when a process I is active, it may send a basic message to process J at any time by sending Bx to J. On receiving this particular message, Bx prime, process I does, it basically updates its clock. Here it will send the clock value. Now if process I is idle, then on receiving this message it will become inactive here in rule 2. Rule 3 says that when process I goes idle, it does two things: it will increase or it will increment its clock, and then it will send the message Rx comma k to all other process, and also it will take the local snapshot for the request x comma k. Rule 4 says that when this particular local snapshot taking message, that is a control message, is received at a process I, it does find out whether the message, whether the timestamp of the incoming message is having higher time than the process I, and also process I is idle. If it is, then it will update its clock, and also it will take the local snapshot for the request which is received by R x prime and x prime. Now if the clock value, which is basically piggybacked or which is coming inside the message, if it is having lesser value, then and I is idle, then it will not do anything. Why? Because the existing process, that is I, is finished or is idle or is terminated after the receipt of message, so nothing has to be done. Now third point here in R4 rule says that if I is active and on receipt of this particular message, then it will not, or it is not terminated, then basically it will only update its clock. Why? Because it is still active, not terminated. So the last process to terminate will have the largest clock value. Therefore every process will take a snapshot for it. However, it will not take the snapshot for any other process. The second algorithm for termination detection is known as the weight throwing algorithm and is given by Huang in 1989. So we will first understand the system model which is used in this algorithm. a process called controlling agent monitors the computation. So if let us say that if this is the computation model and this is the controlling process, so it should have the connection with all other processes, and this is called a controlling agent which will monitor the computation. A communication channel exists between each process and the controlling agent, and also between every pair of process that we have seen in this figure. Initially, all the processes are in idle state. The weight at each process is 0 and the weight at the controlling is 1, whereas here the weights are all 0. The computation starts when controlling agent sends a basic message to one of the process here. The non-zero weight W from between 0 and 1 is assigned to each process in the active state and to each message in the transit in the following manner. So when a process sends a message, it sends a part of its weight in the message. When a process receives a message, it adds the weight received in the message to its weight. So for example, if B W1 is basically carried on the message, so W will be updated as W2, where W1 plus W2 was equal to W initially. So W was broken into two parts and W2 will be retained as its current weight and W1 will be sent. So the process receiving this particular message, it adds its weight in the message to its own weight. Thus the sum of the weights on all the processes and on the message in transit is always 1. So if we can sum all the weights of all the processes for all the process and weights of all the channels, that is equal to 1. So when a process becomes passive, it sends a weight to the controlling agent in the control message. So that is called CW, and this particular weight will be sent whatever to the controlling agent. The controlling agent, which controlling agent adds to its weight. So controlling agent W will add W plus this W2. Now if the controlling agent concludes the termination, if the controlling agent weight will become 1, then it will conclude that termination state of the algorithm. Notations: the weight on the controlling agent and the process is represented by W. Here BW is the basic message which is carrying a weight, and CW is the control message which is carrying a weight from a process to the controlling agent. So this is the algorithm. So the algorithm is defined in 4 different rules here. Rule 1 says that the controlling agent or an active process may send the basic message to one of the processes, say P, by splitting its weight W into W1 and W2 that I told. W1 and W2, they are non-zero. It then assigns its weight W is equal to W1 and sends the basic message with the weight assigned as the other part, that is W to P. On receipt of this particular message, the process P adds dW to its weight. If the receiving process is in idle state, it will become an active. Rule 3 says that the process switches from active state to the idle state at any time by sending the control message C dW is equal to W to the controlling agent and making its weight to W. That means it will return the weight to the controlling agent and basically put its weight as 0. So on receipt of this such messages, which is shown in rule number 3, the controlling agent will add dW, which is coming from different processes to its weight. Now if after getting the weights from all the processes, if summation of the weight is equal to 1, then the controlling agent will conclude that the computation has terminated. Now the correctness of this algorithm. Let capital A be the set of all active processes, capital B be the set of all basic messages in transit, capital C is the set of weights on all the control messages in the transit, and WC is the weight on the controlling agent. There are two invariants I1 and I2 which are defined for the algorithm like this. So variant I1 says that the weight on the controlling agent plus the sum of the weights on A, that is all the active processes, and the weights on all the basic messages in transit and sum of all the control messages in transit is equal to 1. That means entire weight on the system is equal to 1. And second invariant says that for all W, so A union B union C and W is greater than 0. So invariant I1 states that the sum of the weights at the controlling process at all the active processes on all the basic messages and all the control messages in transit is always equal to 1. Invariant 2 states that the weight at each active process on each basic message in transit and on each control message in transit is non-zero. Hence the weight on controlling agent is equal to 1. This will imply by the invariant 1 that the other part, that is WC plus the sum of the weights of the union A union B union C, this part is equal to 0. Why? Because this is equal to 1. Now this will imply that A union B union C is equal to null by I2, because all are non-zero. So hence now since the communication channel is empty, so that is why A union B is equal to phi. This implies that the computation has terminated. Therefore the algorithm never detects a false termination. Further, A union B is equal to phi, that is WC, and WC is equal to 1 by I1 since the message delay is finite, that is after the computation has terminated eventually WC will become equal to 1. Thus the algorithm terminated in a finite amount of time, meaning to say that the control messages which carries the weights from the terminated process will eventually reach to the controlling agent and the sum of all the weights will become 1 within a finite time. Third algorithm, spanning tree based termination detection algorithm. Now we consider in this algorithm that there are n processes, PIs, which are modeled as the nodes of a fixed connected undirected graph. The edges of the graph represents the communication channel. The algorithm uses fixed spanning tree of the graph with the process P0 at the root, which is responsible for the termination detection. Process P0 communicates with the other process to determine their states through signals. All the leaf node reports to their parents if they have terminated, and this is called inflow. The parent node will similarly report to the parent when it has completed processing and all of its immediate children have terminated, and so on. The root concludes that termination has occurred if it has terminated and all of its immediate children have been terminated. Now two waves of the signal generated, one on moving inwards in the sense if this is a tree structure, if the leaves, this is called leaves, and when they terminated they will send the message, and this direction is called moving inwards, and moving outwards, that means if the root sends the message down to the leaf then it is called outward. Initially, a contracting wave of signals called token moves inwards from leaf to the root here. Now, if this token wave reaches the root without discovering that the termination has occurred, the root initiates the second. The root initiates the second outward wave of request signals. At this repeat wave reaches the leaf and the token wave gradually forms and starts moving inwards again. This sequence of events is repeated until the termination is detected. Simple algorithm which we will first understand, and then we will see the problems, and we will, using these problems, we will see the final algorithm. So, the simple strategy is that initially the leaf nodes are given the token. So, they are given token, let us say T1 and T2. Each leaf process after a termination sends its token to its parent, where the parent process terminates, and after it has received the token from each of its children, it sends the token to its parent. This way, each process indicates to its parent that the subtree below is idle. In similar manner, the tokens get propagated to the root. So, when it gets propagated to the root will contain that particular token, and this concludes that the entire computation has terminated after it has become idle and has received the token from each of its children. Now, the problem exists in this particular algorithm. The simple algorithm fails under some situation when the process, after it has sent a token to its parent, which indicates that that particular process is idle, but again receives a message from some other process. So, once it has received a message from its process, then the idle state again will go to a terminate state, but its parent is knowing that that particular process is idle, which could cause the process to again become idle, and that is shown in figure 15.1. In 15.1, you can see this particular situation, that after 1 has given its token to its parent, the node number 5 has sent a message back to 1. So, 1 will again become from idle, it will become an active, but this parent knows that 1 is idle, which is going to make the contradiction. So, this kind of problems is now corrected, and the final algorithm is given by the Topor in 1984. So, the main idea is to color the processes and the tokens and change the color when the messages such as we have shown in figure 15.1 are involved. The algorithm works as follows. Initially, each leaf is provided with a token. The set S is used for the bookkeeping to know which processes have the token, hence S will be the set of all leaves in the tree. Initially, all processes and the token are colored white. When a leaf terminates, it sends the token it holds to the parent process. A parent process will collect the token sent by each of its children after it has received a token from all of its children, and after it has terminated, the parent process sends a token to its parent. A process turns black when it sends the message to some other process. When a process terminates, if its color is black, it sends black token to its parent. A black process turns white after it has sent a black to its parent. So, let us understand the entire algorithm through this particular example. Now, as in the algorithm, you have seen that all the leaf nodes are given the tokens initially, token to the leaves. Now, when these leaves finishes their computation, they will send the token to the parent. So here you can see that this particular node and this particular leaf, they have finished their computation, so they have sent their token to its parent, so this will become an idle. And the set S initially, which was having 3, 4, 5, 6, because they were having token, now the active set of processes will be the process 1, then 5 because it is having token, and then 6, and node 3 and 4, they have become idle as far as the working of the algorithm. Now this one has received the token from both of his children, so it will send this particular token to its parent. So T1 will send its token T1 to the parent. So now the parent will know that the underlying subtree is terminated, that is it's idle, and the set of active states S will be now the node 0, node 5 which is having token, and node 6. Now the algorithm will monitor them. Meanwhile, node 5 has generated a message for the node 1. Now node 1 from idle state, it will become an active state after receiving this particular message, although this token represents that one is active. So the node which sends this particular message, that node will become black in this case, and once this particular node which is black finishes its execution and is idle, then it will send the black token to its parent. And become white then in that case. So here the node 5 becomes white, but it had sent a token, that is T5 is a black token. Similarly 6 has sent its token to this parent. Now the active states are 0 and 2 here in this case. Now when this black token finally reaches to the node 0 and node 2 become idle, now S, the active states is only S. Now node 0 will understand by receiving the black token that there is some message communication. Hence the distributed computation is not terminated. So by taking this black token, node 0 or a root will again send the outward token, and this outward token will propagate the token down to the leaves and restart the entire process again. So in the second round, if let us say that if the computation is terminated without any message exchange, the root may get all white tokens back, and this will be the terminated state. If in the second round also, if it receives a black token, then again this particular process iterates till it receives a white token, and that is the indication that the algorithm is terminated. Now performance, the best case message complexity of this algorithm is of the order n, where n is the number of processes in the computation, which occurs when all the nodes sends all the computation messages in the first round. Worst case complexity of this algorithm is of the order n times m. M is the number of computation messages exchanged. So this, if only one message is exchanged, then basically it will 2 times, 3 times, and so on. So number of times this algorithm iterates outwards, inwards, depends upon the number of messages. Conclusion: determining if the distributed computation has terminated is a fundamental problem in distributed systems. Detection of termination of a distributed computation is a non-trivial task, since no process has the complete knowledge of the global state, and also the distributed system does not have a common clock. So, a number of algorithms we have seen have been developed to detect the termination of a distributed computation. Why? Because it is going to be used in many applications. These algorithms are based on the concepts which we have seen here, the representative algorithms based on these concepts of snapshot collection, weight throwing, and a spanning tree. So, in this lecture we have described a set of representative termination detection algorithm. In the upcoming lecture we will discuss about message ordering and group communication.